Okie dokie. Here we get to the modern periodic table. Very exciting how we organize and group the elements. And here's a really cool picture of the elements, pictures of them. And we're going to look at the periodic table and how they organize it and how they place it. It's not just some random, okay, let's just put this here, here, here. There's really a beauty behind how they made this table, and it evolved over years and years. It all started with Dmitry Mendeleev, a Russian chemist and teacher. He published a table of elements, and this is a picture of him, and he looks strangely like I do. And if I grew my hair out, that's probably what I would look like. So he arranged the elements in order of increasing atomic mass. He had the lightest to the heaviest. Now, when a guy named Henry Moseley came along, a young chap, didn't seem to live that long, unfortunately. 1913, rearranged the elements in order of increasing atomic number. And that's the basis of our current periodic table. It's an increasing atomic number, which means the number of protons. So he kind of rearranged Mendeleev's table, and that's really what we're using today. And still, after Moseley, it's still evolved. So let's just look a little bit at the periodic table. So it's numbered 1 through 118. Now, all these U numbers, we'll get to that first. These have been discovered, but they're called U's. They all begin with U because a name has not been agreed upon. They have to go through these various committees before they come up with a name. Now we have these different blocks here that we'll talk about as well. Now, up till atomic number 92, uranium, these are all naturally occurring elements. Past 92, 93 on are actually man-made. And the thing is, most of these do not last very long. If you look here, solids. Now this is also in your Chapter 6 OneNote folder or tab. These black ones are solid. The black letterings are solid. Liquid are green. So we have liquid here, bromine and mercury. Now that's at room temperature, which is considered around 70, 72 degrees or 20-some degrees Celsius. Now, interestingly enough, gallium turns to a liquid at about 85 or so degrees Fahrenheit, which is about 30 degrees Celsius. So, in fact, it depends on where you're at. If you're in the desert, of course, that's going to be melted. Now, where I used to live, it was 90 degrees in the summer, so gallium would have been liquid. If you hold it in your hands, if you're at 98 degrees, it's going to be liquid. So the thing is, all of these that are solids have some melting point. Usually they're hundreds and hundreds of degrees. Now if it's green, it's a gas. So notice these non-metals here are mostly gas, hydrogen. As you can see, most elements are solid. Synthetic, that means they are man-made. Now notice here, technetium and promethium. Those are not man-made, but they are radioactive. They are unstable. So the organizing principle is the properties of elements are used to sort them into groups. Now the groups are important. We don't just have this random atomic number 1 through 114. We actually have them are organized into groups. So, what are groups? What are the columns? What are the rows? What are the periods? What do we call the columns? That's up and down. Think of the Greek columns. You go up, the little Greek columns, though. Up and down are the columns. If you've ever been to Greece or have seen pictures, there's the columns, up and down. Okay, columns hold things up and down. So what do we call those columns? We call them groups. Groups, so, okay, there it is. Or families. So just like your family group here at Sacred Heart, you're in the yellow, I'm in the orange family group. Very exciting. So family group is the same as column. So you might hear a reference to the same group or the same family. We're in a family group like orange, and we'll get to the different groups. Now what about the rows, left and right? So rows, as you know, you sit in rows in school, left and right. What are the rows called? Periods. Every period you sit in a row. So first period you'll sit in a row, second period you go sit in a row. Well, actually that's not true here. Most schools it is. In chem class it is. You sit in rows. Periods. Okay, so here are the columns or groups, and here are the rows this way, or periods. Now how can we remember that? Well, column looks like a G, and then row looks like a P. Okay, they're very similar. PR, period, row, column, group. They look the same. Column and group look the same, or C and G look the same, and P and R look the same, except for a little difference. So that's how you can remember. A column is a G, a P is an R. So periods, what does periodic mean? Having or being marked by repeated cycles. And that's what you'll see in the periodic table once you look at it. Once you'll see the amazement of it, it's repeated. The same things are repeated over and over, and it's periodic. So we'll see through our study of the periodic table that the rows, there's periodicity to them. You'll see that they're very, very similar. And even if you look at this, you can probably, without me telling, see what the similarities are and how it is periodic. Now the groups, there's two different numbering systems for the groups. The first numbering system, we have 1 through 8, and each number is followed by either an A or a B. Now the groups labeled A are the main groups. These really are the main groups we're going to look at in this class, 1A through 8A. That's where basic beginning chemistry is learned. And these are called representative elements. They represent. So the main groups represent. Okay, you're not going to represent if you're not main. So if you see someone in the hallway, you say you'll represent because they're main. Okay, that means everyone, but everyone here at our school represents. They're all cool, right? Now, representative because they possess a wide range of chemical and physical properties. Now, the groups designated with a B, 1B through 8B, are found in the center. Transition elements. Okay, they transition from one representative to another. So those are the transition elements. So we'll talk about, or we're often referred to either representative or transition. So we'll mostly be talking about we'll mostly be talking about representative elements. Now a more recent numbering system has been devised, 1 through 18. And you will see periodic tables with both those numbers. 1A, 2A, here's the B's. Okay, those are the A's. Okay, here are the B's. And here's 1 through 18. And I really think the 1 through 8, the Roman numerals, really are the easier way to understand things when we first begin. But as you can see, the B's, these are the transition elements. Okay, these are all the transition elements right here. They're the B's. They B, transition. Now, all these A's, where the yellow highlight is, are representative. and it's really the representative that we're mostly going to spend time with. Now I just want to talk a little bit about valence electrons. We're going to hear this a lot in chemistry. It's very important. I'm going to get much more into it later. The valence electrons are the very outermost electrons. And now these are involved in bonding. So if we have this atom here, we have maybe 2 electrons here, and then we have, let's say, 3 electrons here. These are the valence electrons. Those are the valent shell. Those are the ones that are involved in bonding. So it's the outside that matters, just like people. The outside matters when it comes to chemistry. So if you see some dreamy teen idol, it's the outside that you like, right? You don't care about the heart or anything. We like the outside. In fact, there's a website called chemistry.com, and it's not about chemistry, it's about a dating site. And I guess if you go on it, you look at pictures of a dreamboat, and if you like what you see on the outside, you contact him, see if you can have some, if there's chemistry between the two of you. Really, of course, I'm just being facetious there. But the proton, or the nucleus, does have effect on it, because once you see on the outside what they're like, it's the inside. Remember, it's the nucleus, the number of protons that say what sort of element that is, and it's like the protons, the nucleus, that's the heart of the person. All right, so the chemistry might come from the outside at first, but it's the inside there that helps with that all outside thing. But I'm just talking myself in circles now, so let's just move on. Just for chemistry purposes, not dating purposes, the valence electrons, the outside energy electrons matter the most. And let's look at this. So where do we find the outside energy electrons? Well, the cool thing, the amazing thing is, the awesome thing about the periodic table of elements, one of the way it's arranged is by valence electrons. Those in group 1A have 1 valence electron in their so they have 1 electron in their outer shell. All of these have 1 electron in their outer shell. Group 2A, they have 2 electrons in their outer shell. Now we're going to skip over the transition because they're kind of quirky and goofy and different. Let's go to 3A. These guys have 3 electrons in their outer shell. 4A have 4 electrons in their outer shell. 5 electrons. 6A have 6. 7A has 7 electrons in their valence shell. So outer shell is valence shell. And 8A have 8, except for helium. Helium is the exception. It has 2 electrons. The reason why it's there is because these are all noble gases. They are stable at 8. 8 is a filled outside electron shell. It's the valence shell that dictates their chemistry and how they act. Those with 1 valence electron are going to act differently than those with 2. And those with 6 valence electrons are going to react differently than those with 3 valence electrons. It's just like what you wear on the outside. If you wear a garbage bag, you're going to act different than someone who wears a trash can. You can try that. See how people react to you. If you wear a garbage bag as opposed to a trash can, you react differently on what you wear on the outside, and these elements will react differently to the number of valence electrons. It's all about the electrons.